My screen is visible.
Yes, sir.
Okay. So today we'll discuss about 2-3 things, particularly algorithm or app classifications based on data access optimization or data access pattern. Then we'll move towards multi-threading and OpenMP. So in your OS course, mostly people read about multi-threading, but in general, no one teach about OpenMP. Okay, so multi-threading and OpenMP both are shared memory programming model, threading programming model. Okay, so multi-threading is actually basic one is actually mostly manual parallelisms, and OpenMP is automatic parallelisms. Okay, so automatic means compiler using compiler directives with minimal effort. You can do write parallel code, and we can run on multi-core processor, and you can get performance. Okay, so that we'll discuss. Let's start with our things, app classifications based on data access pattern, not data access optimization, but data access pattern based on data access. And then we'll move towards threading, particularly Pthread and locking we'll discuss. Then OpenMP, auto parallelisms using directives. So how, without putting much effort or very easily, we can write parallel code. And then we'll move towards MPI. So next 3 classes will debate on this, particularly coding, so parallel coding. Then we'll move towards our standard, what I can say, resource management methodologies. So our 75% of the lectures will consider resource management. Okay, and this 25% initial data access optimization, serial code optimization, Pthreading, OpenMP, it constitutes of initial 25%. Okay. So algorithm classification and access optimization. So if you look at, so suppose you have some streaming code. Okay, so and suppose order n out of order n. If number of arithmetic operations and data transfers, load and transfer proportional to the loop length, then we can say that application such. We can classify that application as order n by order n algorithm or order n by order n app. Optimization potential is limited, means scalar product, vector add, sparse matrix vector multiplications. These are the kind of applications which can be categorized to order n by order n class of applications. Okay, and memory bound for large n. So simple vector add. So vector add means, let me write the code for the vector add. So for I is equal to 0, I less than is equal to n. N is very large. Okay, I plus plus, and AI is equal to bi plus ci. Okay, so this is the code. So if you look at number of operations inside this for loop, so inside the, so how many data access we are doing? So if you look at 3 read and 1 write, so 3 plus 1, so total 4 data access. Okay, 4 data access we are doing. And what is the floating point operations? Operation is n. So 4n, okay, data access we are doing, and 1n operations we are doing. So in this way, we can classify this kind of code, vector addition code, as order n by order n kind of applications, class of applications. So number of operations and number of data access. Okay, so in that way we are classifying. So number of arithmetic operations divided by number of transfer or access. Okay, and this is one kind of applications we can classify like that. So scalar product, vector add, sparse matrix vector multiplication. These are the actually kind of applications where it can be classified as order n by order n. So order n arithmetic operations divided by order n load store. Is this clear? Yeah.
Sir, is it like the code balance or the intensity we have done?
No, look at code balance intensity, we calculate in terms of finder number. So in earlier case, so if you look at that, I have removed that thing, I think so, that code. So if you look at code balance is we put in terms of number, but here we are putting in terms of order. So exact value and numbers order are completely different. So here we're looking at order. So 4, 3, we don't care. Are you getting a point?
Yes, sir.
Okay, so little bit of going up. Okay, and if you look at this kind of code, then this is actually memory bound code for large n, and compiler can generate very good performance, achieve good performance by using software pipelining, loop nesting, and then whatever I told once yesterday in our class that because this is actually very serial code, so that cache we can take benefit of prefetching, and compiler can do a very good software pipelining using prefetching. So software pipelining, it uses actually prefetching. It try to what I can say, balance the what I can say computations and communications, or computations and data access. If you can balance that thing, you will get achieve a better performance. Okay, software pipelining, they try to do that thing. Next one is if you can increase. So suppose you will get in terms of actually what I can say optimizations. So if you look at this code, so first code, first for loop and second for loop. So first for loop, if you look at 3 word per one floating point operations. This one is what I can say for this loop, first loop. So what are getting actually, we require to transfer 3 word, or in this case actually if you look at 4 also, if you add the, suppose you are using write not allocate, then in that case 3, otherwise it will be 4. In this case, suppose you are using write not allocate, you are getting 3 word per one floating point operations, and in this case also 3 word per one floating point operation. Okay, so but in this case this bi are common, in both the cases bi are common. So how to optimize? In this case, if you can optimize this code, so suppose you just fuse both the for loop, then in that case slightly better you will get. So 5 word per 2 floating point operations. Okay, so this is order n by order n. You can actually, if you want to optimize, and this kind of optimizations in compiler people do, or you can write the code so that at least you will save one access. Okay. So straightforward loop one.
Sir, the lower order n is the size of loop here, right?
Yeah.
The lower order n by order n, that represents the loop size, right?
Yeah, that depends the loop size.
And
The
the
first
upper,
order one is actually number of operations. Okay.
okay, is it number of operations or
Second one
number
is number of data actors. In terms of I mean, what I can say, complexity wise. Okay, order, in terms of order, so we are not changing.
No, but which one is it? The floating point operations or data transfers at the top or upper order n?
Upper order is operations.
Okay, fine.
Second one is actually data transfer. Okay, so order of n square by n square, operations by data transfer. So typical 2 nest loop with stripe count n. So order n square operations per order n square load store. So if you look at dense matrix vector multiplications, matrix additions, matrix transpose. So these are we require order n, means we need to perform order n square operations, and for that we require order of n square data transfer. Simple. So if you do matrix additions. So matrix additions. Suppose matrix size is n square size, n cross n. Then matrix additions, what you need to do? So matrix additions means
So, sir, n should be the total size of input. Like if a matrix is n cross n, then
so in this case n cross n we are saying. So n cross n, n cross n, and n cross n. So n is row size and column size, suppose. So in this case we require to transfer. So So this many data also we need to transfer. So three n square data transfer we require, and how many operations we are doing? N square operations. So ultimately 1 n square and 3 n square. So this is actually, this application can be categorized as actually order n square by order n square applications.
Sir,
This is how you can categorize what you can say applications as which kind of category classifications.
so sir, so what do we mean when we say capital N? Is it not the size of the input? Because size of input is n square.
The small and capital and here in this case same. Both are
Okay.
same. Okay. So this is and this kind of code particularly. So
Sir, what is MVM?
yeah, matrix vector multiplications. Matrix vector multiplications. Matrix addition, matrix transpose, matrix vector multiplications. A matrix is there and another vector is there. This code is for matrix vector multiplications. So Aij is actually matrix and B is actually vector, and we want to multiply matrix and vector. Okay, so if you multiply a matrix with vector, so then what will be result? So it will be matrix vector multiplication. So it will be another vector. Okay, and row of A and vector of B. So row of A and vector of B, and for each case, and you will get another vector, C vector. And originally, if you look at this thing is 2W by 2F. Okay, so because of additions. Okay, but ultimately, if you can reduce, then because of cache, both are row access. Because of row access, it can be number of access, particularly going to memory, may be reduced. Suppose M is miss rate of cache, then we can say 2W into M. So because only for miss we need to go.
Excuse me, sir.
Yeah.
So we are storing a CI in temporary variable, and then we are rewriting temporary variables. So that storing is useless, right?
Which one?
So first line in the first follow.
So first for loop. So this
We are
is for
storing.
okay. So this is actually time is equal to time plus. It should be plus equal to.
Yes,
Sir,
yes.
It should be time is equal to 10 plus. Okay. This should be time is equal to 10 plus. Okay, so that's right. So there is a mistake. So because of that thing, two floating point operations also it is not coming. Okay, so that should be time is equal to 10 plus. Then only it possible. It's fine.
Yes, sir.
Yeah. And this is another kind of means order n cube by n square. So order n cube operations and order n square load store. So clearly this example is matrix vector multiplications. Okay, so matrix vector multiplication, how we do? So in general, kind of suppose this is equal to this is a vector. This one is a B and C. Then what do we do? We take a row and we take a column, and then we get a Cij element. Ith row, jth column, and we get actually Cij. And we need to repeat this thing for how many times? Order of n square time. So ultimately, it requires order of n cube operations, and number of data load store will be order of n square. Okay, so this is order n cube by n square. So we can classify matrix multiplication as order n cube by order n square type algorithm. Order n cube operations by order n square data transfer. And because of this region, order n cube by n square, number of data transfer, mean matrix multiplications, number of operations is order of n cube, and number of data transfer is order of n square. Because of this region, suppose you want to suppose you want to accelerate the matrix multiplications, then you transfer the data to some other place Okay, and do the comparison and get back the result. Still, you will get beneficial because we require order of n square data transfer, but time is order of n cube. Suppose n is very big. Okay, so still means you transfer the data to one places, you do the computations very fast and get back the result. Because number of computations is order of n cube, still you will get beneficial. So have you ever used GPU? Any one of the student or any student?
Yes, sir. Yes, sir.
Have you ever used GPU? In GPU, how we do? So in general, we send the data to the GPU, do the computation on GPU, and get back the result. So this kind of computation is very good for accelerations because we are sending order of n square data, computations we are doing order of n cube, and getting back order of n square data. So total overall data transfer is less and computation is much higher. Suppose n is 1000, that means ultimately you can say if your accelerator can do 100 times faster. Okay, but data transfer, if you do it on your own, then you are taking 1000 times extra. If you can suppose your accelerator is 100 times faster, still you are saving a lot. Are you getting a point? Hello?
Excuse me, sir.
Yeah.
Sir, why?
Why? So I'm not able to understand your question.
Hello, sir. Am I audible?
Yeah, audible.
So I was asking, so why are we studying all these cases separately? Because is it because O of n cube by O of n square, my operation is dominated by the number of operations, the floating point operation. That's
So
why,
number
right?
of operations is dominated by number of data transfer.
Okay, and how are we going to optimize this?
No, how we are going to optimize this kind of applications is well suitable for accelerations. So remote acceleration also, because data transfer is less, computation is much higher.
Okay, like GPU and everything, right?
Yeah. And another thing is this kind of data transfer, because of number of data transfer is order of n square. Even if you want to do caching also, suppose you have a some kind of processor where cache can fit order of n square data, then you can do actually very good computation because you have a number of computations order of n cube. Okay, and in matrix multiplications, suppose you can do means do a either loop interchange or you do a what you can say divide and conquer kind of things. Small part you can fit into means your cache and do the computations. So particularly, have you heard about the Streisand multiplications algorithm? So it divides
yes,
the
sir.
Yes, sir.
yeah. So it divides the bigger one. So it divides the bigger matrix into smaller parts. Okay, smaller part, then smaller part. Okay, then smaller parts. So you divide the matrix into smaller part, and they do the matrix computation in a smaller part. That means if smaller part can fit into a actually cache, then you can do efficiently. So that's why Streisand multiplication is actually divide and conquer approach, and it divides the matrix into smaller size and do the computations. Inside that, it do order of n cube computations. So that's why Streisand multiplications, even if this complexity, what is the complexity of Streisand multiplications? You know,
N power log base to
n
7.
cube.
not n cube. It is not n
N
cube.
power log base to
N bar log
Standard matrix
2.8
multiplication order of n
something.
cube. I
So it
think
is
the
2.8.
2.71.
2.71, yes.
2.71. Even if it in term of order 2.71, so this is theoretical one, but actually you will get very good performance because it is divide and conquer, and inside a small part it do the order n cube computations. It can fit into cache. Are you getting a point? So that's a Streisand multiplication. In general, it is faster. So similar kind of things in general in high performance computing. Why? Have you heard about quicksort?
Yes, sir.
Yes,
Yes, sir.
And have you heard about the heap sort?
Yes, sir.
Heap sort
Yes,
and
sir.
quicksort.
Yes,
Okay.
sir.
So just 1 minute. So first one thing is heap sort. Okay. And another is quicksort. So heap sort and quicksort, what is the time complexity?
So heap sort it is n log n and quick sort worst case n square.
And it is order of n square. It is worst case. But average case, what is the things?
N log n.
N log
N
n.
log n. Most of the time it have actually n log n. But this one is order of n square worst case. And this one is for all the cases heap sort, it is n log n. Best case, worst case, and all cases it is n log n. Okay, so why still named this quicksort as quicksort? Many times they could have used heap sort because heap sort is actually very good. Means all complexity is n log n. But why they go for quicksort? Quicksort is really faster because quicksort, it's actually if you analyze the things, then the constant come out is smaller as compared to heap sort. Also, another thing is quicksort use divide and conquer approach, and divide and conquer approach sometimes it actually feed into the cache, and number of hit miss will be much lesser in quicksort. So that's why they named this particular sorting, okay, as quicksort, and most of the internally they use quicksort algorithm.
Sir, why is it better than merge sort?
Even merge sort it use extra array. Merge sort it use extra array. Space wise not good. Quicksort is it uses less space
In place.
in place. And another thing is it's if you analyze theoretically also its constant is much smaller. Also, third most important point is it uses divide and conquer. Because of that, actually it fit into cache and number of hit miss. Actually, it run faster than any other sorting. So that's why they named as quicksort. So it takes benefit of
This last
cache.
part. Could you repeat this? Why? Why will it fit in cache?
So because of divide and conquer, so number of hit miss will be much lesser. And whenever you divide in smaller pieces may fit into the cache, and it can result actually a lesser number of misses, cache misses.
Okay.
Are you getting a point?
Yes, sir.
Yeah. So because of that, it's named as quicksort ultimately. Okay. So in regular C++ or C in standard algorithm, whatever the in STL, so they use quicksort by default. Okay, so let's move towards other things. So where this algorithm classification, app classification is necessary. So that we have discussed. Now we'll move towards standard our other things, multiprocessor programming using threading. But let's start with new topic. So 3 topics we'll cover: programming part, particularly threading, OpenMP, and MPA. So in next 3 classes we'll discuss this thing, and after that we'll have a quiz, and it will be pre-announced quiz. Not in the next week. Next week we'll have a pre-announced quiz. Please mute yourself. Okay. So we're getting some noise. So threading language and support. If you look at initially, so threading used for multiprocessing on a single core. So earlier days, multiprocessor was not common. So everywhere they use single core. And earlier days, multiprocessing on a single core, threading used for mostly for multiprocessing on a single core. So filling or simulation of doing multiple work simultaneously, even if you have only one processor. So earlier days, even if you have one processor, still will simulate or will think like that we are doing multiple work simultaneously, even if we have one processor in our underlying hardware. So means earlier days, before 2004-5, okay. So most of the computer have only one processor, and they used to increase frequency and other hardware, but they don't used to increase core. And they use time division multiplexing or time slicing, or in very layman term, we can say it is interleaving. So time interleaving. So for sometimes process A will do, so after some time process B will do, then after some time process C will do. So time interleaving wise they will do the process, and the time interleaving will be very, very small. It will not be noticeable for human, and human will feel that many work is getting done simultaneously. Okay, so this was initially threading was used for that, but nowadays threading mostly used for to take benefit of multi-core. So most of the times our architecture is multi-core, and why not to use multi-threading? Okay, we can take benefit of multi-core, and it may improve the performance. Also, it may improve the energy efficiency, and we can use both TDM, time division multiplexing, whatever we used for time slicing or interleaving for single processor case. So to simulate multiple work on one processor, that same thing also can be used here. Also, you can do space division multiplexing. What is space division multiplexing? At different time, different worker will do. Okay, that is space division. And this time is one guy, so he will do different work at different time. The time division multiplexing. So we can use both TDM and SDM. Means suppose you have multiple cores. Okay, so 10 cores. Earlier you used to have one core and 10 work. Okay, nowadays 10 core, maybe 20 or 25 works. So this 25 work run on 10 cores, not one core. So we can use time and space, different work on different processor at different time. Okay, so in that way you can manage, and you can get a higher performance. Also, we can get energy efficiency, better energy efficiency. So better energy efficiency, I already told in the first or second class. So if you run a processor at 3 GHz, then it will consume huge amount of power. But if you run the multiple core at 1 GHz or lesser speed, then your energy efficiency will increase. So in that way, it is energy efficient also. Is this clear? Hello?
Yes,
Sir,
sir.
could you repeat space division multiplexing again? What is space division multiplexing?
Space division means you have multiple processor.
Okay, so like horizontal scaling in a sense.
Yeah, horizontal scaling. So you have multiple. Earlier it was only one core. You have multiple core.
Okay.
So time also and space also you can divide a process on at what time at what core.
Okay.
Okay. So that will discuss the time and space more detail. Okay. So we have whole 75% of the whole course, HPC course is reserved for space, TDM and SDM. So scheduling will be discussed very, very thoroughly. Okay. So rest 75% of the course will be based on this TDM and SDM. So don't worry. Okay. So yeah.
Sir, how threading is more energy efficient since more cores will consume more energy?
No. So more cores consume more energy, but you can run at lower frequency.
Okay.
You can run at lower frequency. So have you heard about this recently some movie launch, some Udan? Okay. So in that he shows that why to go for a very big airplane. So smaller airplane means smaller chidiya. Okay. So it will consume less, but it can also go up to lesser height, but almost efficiency will be more. So kind of boiler chicken, or you can say one eagle and one sparrow. Okay. So 10 sparrow and one eagle. Okay. So if you look at sparrow will be more energy efficient. Kind of things. It is multiple cores, but smaller. It might be energy efficient. Okay. So in your mobile, so you have actually 8 core, but very small core. But in your PC, you have 4 core, but they are very jumbo core. So PC are actually not energy efficient, but mobile are energy efficient. So larger number, smaller core will be mostly energy efficient. Okay, and nowadays most of the mobile also what they're putting efficiency core and performance core. So have you heard about this term? Efficiency core and performance core. Efficiency core means it will run at smaller and lower frequency core, and performance core means it will be bulkier and it will run at higher frequency. So even Apple A15, so recent one, or M1. So what that is not homogeneous. So some are actually performance core. That means bulkier and run at higher frequency. Along with they will augment some smaller core run at lower frequency, so that they will get efficiency. Whenever you require performance, run on performance core. Otherwise, most of the time you try to manage it efficiency core.
So, sir, is it like saying that RISC-based processors are energy efficient but less powerful?
look at, yeah, means nowadays rigs are also much powerful. If you look at M1 is edge powerful edge compared to our Intel processor. Apple M1. So it is RISC based, ARM based processor. It is based on ARM architecture. Okay. ARM means advanced RISC machine, and it is powerful. And another most important thing. So most of the Pentium processor, they are using 6 instructions, but internally they convert. There is a virtualizer which convert the 6 instruction to RISC instruction, and internally they execute RISC instructions. But they are continuing with their legacy. Okay, so that is a different thing. But internally, still they are using RISC instructions, and RISC instructions are actually, it is easy to pipeline, and it is energy efficient. So Intel means already means they started the things of this x86 instruction, and they are continuing with their legacy. That is different issue. Okay, so now we'll move towards threading language and support. So mostly there are 3-4 things most popular in Linux environment. So we have Linux or Unix, whatever say. So popular one is POSIX thread, and POSIX thread can be installed in Windows environment also. And it is popular, initial and basic one. And if you know the basic one means high level things also, it can be possible, and it is not very difficult. And with C++ thread, so improved construct for threading, available in C++, 11, 14, and recent C++ versions. And Java thread have very good memory model, particularly atomic functions and mutex, particularly locking protocol, and particularly serializations and memory model is very good. And after that, why you write threading code manually? So suppose someone have written already serial code or C code, why not suppose some for loop is there or some standard looping structure is, why not to parallelize automatically if possible with compiler directive? So that kind of things done with actually OpenMP and Silk. So OpenMP is very easy to do. Silk also it is not very difficult, but Silk use dynamic parallelism. OpenMP use static parallelism, but loop based, very high level loop based, and both are what I can say shared memory parallelism model. Okay, shared memory parallelism model. OpenMP and Silk. We'll discuss OpenMP mostly. Silk also in this class. Okay, and Silk is developed by. Have you heard about this algorithm book? Which book you follow?
CLRS.
CLRS. In CLRS, have you heard about one chapter, multi-threaded algorithm?
I saw that in the time.
So in actually means CLRS book. So there is a chapter called multi-threaded algorithm, and this Corman, Lisserson, and Rivest, particularly Lisserson. So Lisserson is main guy who actually wrote the paper. He is the man. He's from MIT, and his most important research work, seminal research work, is based on actually multi-threaded algorithm. And even in algorithm books, he wanted to include this chapter. Even if it is not relevant, he wanted to include the multi-threaded algorithm. And that's why this Silk whole philosophy and whole algorithmic design is included in Saylor book. Okay, so because he is the main researcher behind the Silk, that's a multi-threaded algorithm. So that's why this chapter is included in the Saylor book. His own work. The rest of the things he took from different people and different book, but that is his own work. Lisserson's own work. Okay, so thread pooling at high level management, thread management. So without looking at the detail of threading, so you can write code at high level, C level, and compiler or very high level parser will automatically take care of parallelism. So without putting a lot of effort. Okay. So these two things we can discuss. Okay.
Excuse me, sir. Sir, using multiple slow cores instead of a single fast core, is it just better in terms of energy usage, or is it more like it's better in terms of performance as well?
So both. So most of the time we don't require performance. Okay. But whenever you require, use it. But most of the time we require energy efficient core.
Okay.
So that's why combining both is a better choice.
Okay, but isn't performance more important in general? I mean,
So in HPC domain, maybe a very high domain it's essential, but most of the common domain we don't require. So
okay.
most of the time we require energy efficient core, and very less time we use for this thing.
Okay, but still
So
it's better in terms of performance also, right?
yeah,
Do you think? But okay, thank you.
but overall there is a trade-off. Overall there is a trade-off. So if you look at the Apple iPhone, so Apple iPhone they have actually 2 performance core and 4 efficient core. Performance core means they is bulky and run at higher frequency. Okay, and 4 efficiency core means it is energy efficient core. So that can be managed as all general purpose kind of thing, and that performance core will be used for what you can say your PUBG kind of thing. So most of the time they will not be used.
Okay, sir.
Okay. Okay, so Pthread, C++, Thread, and Silk and OpenMP. This one slide will give you whole big picture of this thing, but font may be much slower, but because it is online, so and I'm not using Blackboard or projector screen, so computer screen is fine. So this is actually very are you able to see these things? So this is the creation of 2 threads. Okay, and function 1 we want to execute function 1 and 2 on 2 threads, and this is a pthread model. We write code in this way. Okay, and C++ thread is little bit of higher, so directly you can declare a thread t1 run functions on 1. So create another thread t1 with t2. This is t2, then fun2 function 2 with some parameters. This is a C++ there, and C++ have directly some functions t1.join, t2.join kind of things. This is very high level, when it's a kind of a little bit abstract. Its abstraction is higher. So thread is abstracted to little bit higher level. Okay, and this is very basic functions in C, but internally almost it do similarly. Okay, so internally it do similarly, and in OpenMP. So we don't write thread all the things. So what do we say? Pragma OMP parallel for, and suppose this kind of code is there, and we know. So this is for ith iterations. It is independent for each I is equal to 0, 1, 2. If for each iteration it can be run independently. So if you give the compiler some options using this some directive, this is called compiler directive. Pragma OMP parallel for. So try to parallelize this for loop. And we know this is from the code itself, so we know can be parallel, it can be parallelized. So try to parallelize it. So it auto converts serial code into threaded code. And how to compile? So if you compile using gcc app openmp test.c, then it will try to parallelize the code. And suppose you run an export omp number of threads you will 10, and then simply run a.out, then it will try to run this code on 10 threads. So here effort is very much less. Okay, so effort is very much less, but here it can do for only loop based. Suppose some kind of function based kind of things or nested function based, it will not do. Only for loop kind of things it will do. Okay, and for recursive function kind of things, or what I can say dynamic conquer kind of things, then we want to take parallelism of that. Then there is another tool called Silk. Okay, Silk can take benefit of actually dynamic parallelism. So it can do the DAG, directed acyclic graph or recursive code, and it take parallelism out of that. So Silk is a much higher level as compared to the OpenMP. Okay. So there are clearly 4 type of things. One is basic Pthread, C++ thread, OMP, and Silk. Okay. So in OMP and Silk, so we don't write actually what you can say implicitly we will not write the pthread create or pthread join or pthread which thread to which function will go to which thread. That we don't write. It take care automatically. So this is, we know this threading, so this will go very quickly, this particular thing threading, because in our OS course, I hope most of the people have already done this OS course. So I assume, okay. So if someone don't have any idea of OS, let me know. In OS, have you read about threading? Hello?
Yes, sir.
Yes, sir.
So I assume most of the people have read threading in means OS course. So I'm not going to detail about the Pthread and threading. Okay, so simply I mean not skipping but going very fast. Okay, so I expect people will not ask unnecessary question also. Okay, so because everything so we know that thing. Okay, so about Pthreads and threads, and if we look at programming with Pthreads, then so we need to know about threads, share variables, need of synchronizations, and synchronizing with semaphore, and what is thread safety and re-entrancy, race and deadlock. So these kind of things we discuss in particularly threading. And if you look at traditional view of process and threads, so thread are actually means what I can say lightweight process we say, and process have actually process context, code, data, and stack. So if you look at this is program context, data register, condition code, then pointers. So let me change to will not write much now. So we have this candle context and VM structure, virtual memory structure, and these things. And for each process, we have stack, then runtime heap, then PC. Okay, so these are actually these things we keep track for the process. And for threads, so multi-threaded code. So then process equal to thread plus code, data, and kernels. And if you look at this is main threads, and many things get shared, particularly for different what I can say virtual memory structure. This is memory is shared. Okay, this thing is for whole process how many threads it depends, but for all the threads this memory structure is same. There is shared memory, shared library. Okay, these are all same, and some stack pointer and thread context will be different for different threads, and it share the whole code and data. Okay, that means memory is shared, code is shared, but each thread can have their own some private area also. And multiple thread can be associated with the process. Each thread have its own logical control flow, particularly sequence of PC value. Each thread share same code, data, and kernel context, and each thread has its own TID. So each process have PID, and PID have many TIDs. Okay, and nowadays to run multi-threaded program on actually multi-core. So what most of the OS do, they clone the thread to process, so that in general in what I can say scheduler. So OS scheduler, so that they schedule process. They don't schedule threads. So if they want to schedule thread into process, then we need to clone the thread to process. Then only it can be treated as process and can be scheduled. So a process with multiple threads, you can see. So this is main threads, stacks, and this is the shared things. And suppose that process have another thread 2. Okay, this is a main thread and this is another threads. So
Sir,
yeah.
Sir, what do we mean by cloning threads into process?
Of what you need by the cloning. So
yes,
I cannot say it in detail, but cloning is a process where you can treat a thread as process.
okay.
But it will link to the original process, but this OS will treat that thread as process. Okay, and it will schedule as a process.
Okay.
So that
Okay.
when suppose a process have 10 threads, then each thread will get a chance on individual chance on processor to execute. And logical view of threads, you will get a thread associated with process from a pool appears, unlike process, which from a tree hierarchy. This is a process hierarchy. So this is a Linux process particularly. Okay, so P0, P1, and this is SH, foo, bar. This is some process hierarchy we do, but in threads is actually they appears like peers. Okay, so thread associated with the process from a pool of peers. Okay, so all threads are similar peers. They share all the code, data, and kernel context. Okay, so this is a multi-threaded view, and it is multi-process view. And the standard interface in particularly Linux or Unix, we have POSIX threads, P threads we call, and that's we use for programming P threads. And this is standard, and it's a very basic and standard one. And basic, what I can say, API, application programming interface, APIs or basic functions, just like C have API, printf and scanf. These are API. Okay, so functions, API functions, kind of things. So here for creating thread, pthread underscore create, then joining threads, then determining which thread pthread shall, terminating threads, cancel and exits, then synchronizing to access the share variables. So this is actually 2-3 things: pthread mutex init and pthread mutex log and unlogs. Okay, so these things already you have studied in your OS course. Okay, mutual exclusions we should not discuss here much. Okay, and this is how you can get the pthread hello world program. This is a main program. So in main program, we're trying to create declare a pthread TID, and we're creating a thread and assigning to the TID. Okay, and this is hello. These functions we are calling, and these are the attributes and these are the arguments. So attributes are usually null, but you can put some attributes, and we can have actually some private area. Okay, and this is actually pthread join. We create a threads, and this main program will wait for the thread to create and executes, and then after it finishes the executions, then it's pthread join means it wait for the after creations, it creates a separate thread. A logical view will be like this. So whenever you call a pthread create, then it will create a peer threads. Okay, and in this case, it will run the pthreads and it will wait for this pthread create and pthread join. Whenever we say pthread join in main, then it is actually trying to wait. This main thread is waiting here. Main thread is waiting here.
Sir, can you go one slide back?
Yeah.
Sir, what is the difference between thread attribute and thread arguments?
Thread argument means suppose these functions take some what I can say some arguments. So every function takes some arguments. And thread attributes means suppose you want to associate some kind of other parameters with that. So suppose what area, stack area size. So what are the other variables we want to, some area we want to attach with that. That thing can be done with thread attributes.
Okay, sir.
And pro and cons of threads. So threads are actually easy to share data structure between threads. So logging information, file cache, all the things can be done. Thread are more efficient than process because it share a lot of code and data. Okay, so and creations time is also very less. But sometimes it may not be good for some cases. Unintentional sharing can introduce susceptible and hard to reproduce error. So in case of kind of error or anything, so suppose one thread get some kind of issue, then all thread get blocked. So kind of things. So because many times OS will treat as one process. Okay, so all thread of a process will treat it as one process. So if you one thread get some kind of disturbance from the OS, then a whole process will get stopped. So ease of data sharing, greatest strength of the thread. Also, it is a greatest weakness. So whenever you're sharing some things, so sharing is sometimes it is beneficial, and sometimes it is great weakness also. Suppose you are accessing the shared data, but accessing shared data, if it have a lot of write, then actually it is worrisome. If you are sharing a lot of reads are there, then it is actually beneficial. If sharing with a lot of writes, then we need to take care. So share variable writing. So have you heard about this share? We need to lock the variable, then only we can write. And if you are locking more number of time, many many threads are waiting for writing to shared variables, then ultimately we cannot take benefit of parallelism. So that will be serialized, because at share variable write access, it need to be serialized. And this is example of some threading. Okay, suppose this code we have already seen. So this code already you have seen vector sum serial. So this code already you have seen this thing. And suppose you have 4 threads, 4 processor, and you want to take benefit of 4 processor, then you can write a multi-threaded code. So this is some vector sum serial code. Okay, so how we can do? Because in this case we know, so we can write, suppose size is equal to 1000, and we have 4 core, and we can write using 4 thread very easily. So 0 to 250, 250 to 500, 500 to 750, and 750 to 1000. So in that way you can divide into 4 area, and each thread will work on their own area. So clearly work per threads, size by number of threads. In this case, size is total 1000 and number of thread is 4. So everyone is getting 250 equal amount of work. So divide work into equal number of threads. So this is what we are trying to do. So do vector sum parallelly. Okay, so this is the vector. So every thread will do on each area. So suppose this is lower bound or upper bound. So every thread will get TID. So first, what we are trying to do? So get the thread ID, and based on the thread ID, so size per thread is, we know, total vector size by number of threads, and lower bound is size per thread into TID, and upper bound is lower bound plus size per threads. Suppose size per thread, in this case, B size suppose 1000, number of thread is 4, then size per thread is 250. Okay, so suppose TID is equal to 0, then what will be lower bound? So size per thread into TID. So size per thread is 250 into 0, and then 250 plus upper bound will be 250 plus size of thread, size per thread. Size per thread is 250. Okay, so 0 to 250. So 0 to 250, excluding 250 is excluded. Okay, so for j is equal to lower bound to upper bound, each thread will do their work in their area. Okay, so each thread will work on their own area. So T1 will work on 0 to 249, T2 will work on 250 to 499, T3 will work for 500 to 749, and T4 will work 750 to 999. And this is how do the vector sum, parallel vector sums. So we are creating 4 threads, number of thread is 4 threads. Okay. Okay, so number of thread is, suppose you have declared globally, then it can be accessed in that function also. For I is equal to 0 to number of threads, you create threads, and what this is ampersand thread ID null, then what function we are doing? Do vector sum, and we are passing a parameter argument I, ampersand I. So I here, for I0 case it will be value I, for 1 case it will be 1, likewise. And after doing these things, this thread is waiting. So this is very simplistic code, and in this case the main thread is waiting. So we are creating 4 threads. 4 thread will be executing parallelly, and main thread will be waiting. Very, very simplistic code. Is this clear? Hello?
Sir,
Ah.
I think there is a small issue here. We are passing this address of this I to all the threads. So all threads are receiving same pointers.
Yeah, there may be some issues. So,
Yeah, so
we
they
can
will
create an array. We can create an array, we can assign these things, and then we can do. So there may be some issues in this case. Okay, so what you pointed out is good. So it may not work exactly, but we can create an array. For each one, we put the suppose what you can do. So let me write this thing. So here, another T array. So T4, suppose 4 array, and you assign 0, 1, 2, 3. And in this case, instead of %i, so you pass ti. So this is better. So whatever you ask question, it can be solved like this. Are you getting a point?
Yes, sir.
Now clear your doubt?
Yes, sir.
Yeah. So this is one error. And matrix multiplication and vector threaded matrix multiplications. So in matrix multiplication, what do we do? So suppose this is C, this one is C, and C is equal to suppose ith row and jth column we do. Jth column. We take ith row and jth column. So same thing, divide the whole row into t chunk, and so each chunk contain n by t rows, assume n by t, n mod t is equal to 0. So for simplicity. So this is serial matrix multiplications. So this is there should not be any doubt on this. Okay, serial multiplications. So ijk loop, and what we are doing. So for I1, particularly I, so this will be I is equal to 0 to size. That thing we are dividing into multiple threads. Okay, so for J and K, we are not doing anything. For I, we are changing. Okay. For I loop, we are dividing for different threads. And same calculations. So here TID we are taking and thread size, and this is upper bound and lower bound calculating, similar to earlier one. And we are not doing anything, same thing. Okay. So suppose estimating pi using Monte Carlo. So this is also very simplistic examples. Suppose how you can, what is the definition of pi? Hello. What is the definition of pi? Anyone from front side? What is definition of pi?
Ratio of circumference by radius for a circle.
Its diameter.
Yeah, ratio of
Circumference to diameter.
for
Of a
unit
circle.
circle.
Of any
Of
circle.
unit circle.
Of any circle, sir. The
Yeah.
radius will get cancelled out.
Okay, that get cancelled. Okay, so and if you want to estimate the value of pi, so and you know what is pi is irrational number. We cannot represent it using p by q form. So 22/7 is approximated value, and even Ramanujan kind of people, big people also, they calculate out to some 1,000 or 10,000 digit. They try to approximate, but they are not able to do. But it is not. But we can approximate and we can estimate the value of pi. Okay, some approximate value we can do, and using very simplistic randomized Monte Carlo method. Monte Carlo method is used for what you can say. It is for approximating the things. Okay, so the probability of random variables lying inside circle. Suppose you take a unit circle. So this part only. So this part. This is a unit circle centered at 0. So you take only this part. Okay, so if you take only this part, and if you generate two random number x and y, okay, and instead of random number, let's look at the suppose. So what is the probability of this circle? So if you look at this is area of circle in this part, and this is the area, whole 0 to 1. Okay, so this is actually this area of this square is equally 1, and area of 1/4 of this circle is actually how much? Area of circle. Area of circle is area of circle.
Pi r square. So in this case, it is pi.
Pi r square. In this case, it will be pi. Okay, and this is this area is this is 1 and this is 1. This will be 1. Okay, so total area of all the thing is pi, but this part will be pi by 4. So area by circle by area by square. This is area by this circle by this is will be pi by 4. Suppose you generate any random number x and y. Okay, and its coordinate xy coordinate, it falls this side or it falls this side. If you look at the overall probability, if n is equal to very large, okay, so then its probability will be pi by 4. So this probability of x square plus y square less than 1. Okay, so within this will be what you can say, ultimately probability can be calculated by number of points in this part and total part. And when n become very large, so we can say it is approximated. Okay, p will be p0, and ultimately pi will be 4 into m by n, because this probability will be pi by 4. Okay, and if you calculate what will be value of pi, this pi by 4 and this is mn, so pi will be 4m by n. So this thing's equal, this part and this part. So ultimately pi will be 4 into m by n. So what is m? M is those time the points lie inside the unit circle, so in this part, and n is total number of points, total number of times we are picking up. So we are generating random number x and y and calculating this, okay, x square and y square, whether it is falling inside the circle or not. If it is falling inside, then we are counting, and this is total number of time we are doing, and pi will be double count by this is count by this is a m and this is n. Okay, and after that we are multiplying by 4, and whenever we are doing serially, so it do from left to right. Okay, first it will divide, then it will multiply. Okay, we are not doing bracketing, so whenever we are not doing bracketing, then this is m by n, then it will do the calculation, then it will multiply by 4. This is Monte Carlo pi calculations, and suppose doing for n points, n iterations. Suppose one processor can do 10,000. Suppose you have 4 processor, you can go for 40,000. So if you increase the number of points, then your accuracy will be more. So that is the logic. So instead of doing it one processor, so 10 thread can generate 10 into n points and calculate with more accuracy. So each thread calculate their own pi, and after that average it on later and recalculate pi from the collective m. So that also you can do. So for each thread, we are calculating same things and finally summing up the things. Okay, so this is how we can calculate the Pthread. And these are the 4 or 5 things we have discussed, how we can write multi-threaded program and how we can improve the performance of the system. Okay, so with this 3 example, particularly what 3 example we took? So we took vector additions, matrix multiplications, and value of pi. These 3 examples with how we can write multi-threaded code and get higher performance. Okay, so with this we finish the course today class. Thank you. If you have any doubt, yeah.
Sir, before the quiz, could you perhaps arrange for a doubts class from the previous?
Yes, why not? So we'll arrange for a doubt class.
Okay, sir. Thanks a lot.